So next we look at order of epsilon square. Now once again the domain equations are the same, so I shan't rewrite them. Right? They look exactly the same as we had here, because there is an epsilon in the domain equations. It's only the boundary conditions which deserve attention. So the boundary condition, let's start with that on U at y equal to half. Now let's go back to the Taylor expansion of our most boundary condition. Yes. So now we want order epsilon squared. So starting from here, we should get u2 from here. Because of this epsilon, we'll get dou u1 by dou y surviving from here. And here we'll get dou u0 by dou y square also surviving as an order epsilon square contribution. So we have all three terms giving us a contribution now at this order. So if we rearrange, we get u2 is minus sine 2 pi x over 2 dou u1 by dou y minus sine 2 pi x the whole square, of course, upon 8 times dou square u0 by dou y square. And for V2, of course, we'll get something similar, except we know V0 is identically 0. So all we'll have is minus sine 2 pi x upon 2 dou V1 by dou y. Again at y equal to half. And of course at y equal to 0, we have the same simple boundary conditions that u2 is, dou u2 by dou y equal to v2 equals 0. Okay, so now let's look again. Let's look again at the boundary conditions at y equal to half, because as we saw previously, the entire solution rests on the functional form of the boundary conditions and their dependency on x. So because we know that u1 is basically sine 2 pi x phi1, and we know dou square u0 by dou y square is minus 1 from the 0th order problem, we can simplify this boundary condition and try to see whether we can bring both these terms into the same functional form, so that we can postulate, we can seek a solution on a separable form. If these two terms remain separate, then we'll have to, because the problem is linear, we just have to assume the solution to be a sum of two terms, one with the x dependency of the first term, another with the x dependency of the second term. But let's see how things go ahead. So we'll get u2 is equal to now remember, u1 is phi1 sine 2 pi x, and therefore I have minus sine 2 pi x the whole square divided by 2 times dou phi1 by dou y. This, of course, evaluated at y equals half. And then the second term gives me another sine 2 pi x the whole square. So you see that we have the same functional form, which is nice, times minus 1, of course. But now I can use a trigonometric identity, right? That so we don't want to have this sort of quadratic dependence on a sinusoid. Instead, we want a linear dependence that we can work with, so that when we take the derivative with respect to x, I get a simple functional form. So I can use a trigonometric identity that this sine squared 2 pi x is simply 1 minus cosine 4 pi x. right, divided by 2, which then gives me the final form of my boundary condition as 1 minus cosine 4 pi x times minus 1 by 4 dou phi1 by dou y, the half factors multiplying to give 1 by 4, and plus 1 by 16, evaluated at y equals half. Okay, similarly, let's just check what the boundary conditions on V2 look like and see if it is consistent with this condition on U1. So we know if we look for a separable solution now, we have one part of U2 which must satisfy this boundary condition, which is independent of x, and then we have another part which should go as cosine 4 pi x to satisfy the second part of the boundary condition. So we would like to seek a solution which is some portion which is completely a constant plus some portion which is like phi2 of y times cosine 4 pi x. But for that, the corresponding solution for V should have the outer phase dependence to be satisfy the continuity equation. So let's just check if that holds. So V2 is minus sine 2 pi x by 2 times dou V1 by dou y. But remember, dou V1 by dou y is just minus dou u by dou x, right, from the continuity condition, from the continuity equation. So this gives me sine 2 pi x by 2. So dou u1 by dou x will be cosine 2 pi x, right, into 2 pi times phi 1. Yes, that makes sense. And now I can use another trigonometric identity that basically sine 2a is 2 sine a sine b. So I get pi by 2 times sine 4 pi x times phi 1 at y equal to half. So you see that my solution for V1 now is going to be out of phase with that for U2. Sorry, my solution for V2 is going to be out of phase with that for U2, which is what I want. So then it makes sense. This is consistent with assuming basically a separable solution for U2. So therefore we can say that U2 must be equal to some constant that I'm going to call now E, which is a constant, plus phi2 of y cosine 4 pi x. Alright, that's great. So now we have a form which we know is going to work. We can follow the same procedure as before because the domain equations are the same. So I substitute U2 into the governing equations. I assume a form, of course, for G, right? So just as I had done for G1, I can assume G2 to be some constant C2, this time cosine 4 pi x, right? So then I'll then get an ODE for U2 that I can solve in terms of two unknown constants of integration and G2, substitute into the substitute the boundary conditions, and then use the equation of and then use my condition on the flow rate to determine the boundary condition, the unknown constant C2, and then I can find U2 and go back to my equation for the flow rate. But here again the problem helps us to simplify the calculation for the flow rate, because as we had seen before, the condition that dq dx is equal to 0, right, on this solution would simply imply at this order that dou x of u2 integral dy must be equal to 0, which in turn, when I now will not say anything about the constant part. So the most important thing at u2 which will affect the flow rate is this constant, because this x dependent part will simply lead me to conclude that the integral of phi2 dy from 0 to half must be equal to 0. This would in fact be used as my third condition in order to determine the unknown constant C2 when I'm solving for U2. So I know beforehand that this is going to be the condition on phi2. So even without solving phi2, I now know that the correction to the flow rate, take total flow rate Q, which is Q naught plus epsilon square times integral 0 to half U2, which is E plus phi2 of y cos 4 pi x. Right? I now know that when this integral over phi2 is going to be 0. This comes directly from the fact that q has to be independent of, the derivative of q with respect to x is 0. So therefore, the contribution of u2 that depends on x can give no contribution to the flow rate. So it's only E that survives. So now you see also why at first order, which was entirely dependent on x, I had no contribution. It's because the second order also has a constant part to the solution that I can now affect the flow rate. This of course follows from the details of my solution procedure, but we knew of course beforehand that we should expect to see a flow rate correction only at second order from arguments of symmetry. Okay, so now I can say that the flow rate correction Q minus Q naught, so the change in the flow rate from the base state, is an order epsilon square quantity that is simply 0 to half times E. So all I need to do now is to determine E. I've lost track of which equation number I'm on, but let's call it 8. So all that remains to determine E. But the calculation of E is quite straightforward. Note that it's a constant. So if I substitute U2 into the domain equations, right, because they are completely linear equations, right, so it's the same equations here except I have U2. So the basically this will go to 0 because it's just a constant E. This term goes to 0 as well, and basically it tells me that there is no G1 here, that G1 is entirely determined by the x dependent part of U2. And so E automatically satisfies the governing equations, the constant part. So the only role it has to play is in the boundary condition. So automatically I know that E is basically going to satisfy only the constant part of my boundary condition on U2. So I now know that E is equal to, from my boundary condition that I have here, is just E is just minus 1 by 4 d phi by dy at half plus 1 by 16. Right, so now I just have to, substitute, this is phi1 of course, I already know this. So you can see now that I'm about to determine the change in the flow rate, not only without solving for either v1 or v2, but without even completely solving for u2. Just by utilizing the condition I had obtained on the variation of the flow rate with x, and by understanding the structure of the problem before blindly diving into trying to solve it. Okay, so this is all that remains, so let's quickly do this. So where was I with phi? Yes, I take dou phi by dou y, which drops out this term. I only have a sine h 2 pi lambda, and then y goes as half, so it's sine h pi lambda times a. into 2 pi lambda with a negative sign, of course, because it's a positive sign because it was cos h derivative. So I have minus 1 by 4. I get a 2 pi lambda from the y derivative. What remains, of course, is a sine h times pi lambda after substituting y is equal to half. And then, of course, I had a multiplying it all. And a was 1 by 4 plus, a is all this stuff, so I can substitute that in there. But there's a denominator of cos h, that's important. But now I know what C1 is as well. Right, C1 is this quantity over here. So if I substitute that in also, you can work out the algebra. But ultimately what you will get is the following. And there we have it. This is E. And therefore, the change in my flow rate correction is just going to be E times Y, substituting the derivative, is just half. Right? So the change in my flow rate is just half times E. So now the question of whether the flow rate increases or decreases depends on whether E is positive or negative. So now it's really it's not immediately obvious because you have two terms. One is positive and the other appears to be negative. We can be sure if we take the asymptotic behavior of tan h in both limits. So the function tan h for different arguments of pi lambda. So tan h is always bounded by pi lambda. So if you actually were to plot versus pi lambda, you will see that tan h looks something like this, which asymptotes to a value of 1 as pi lambda increases, whereas pi lambda itself will just increase as a straight line. So you can plot this, or using your knowledge of the Taylor series of tan h, you can convince yourself of this, as well as knowing the asymptotic behavior of tan h, that it tends to 1, because tan h is sine h by cos h, which both become equal at large values of its argument. So what this means is that this term is always positive for all values of lambda, whether small aspect ratio or large. So this is a positive quantity. Tan h is of course a positive quantity, which means that this is indeed negative. Now the question is whether this term is going to be larger than 1 by 16 or smaller. So you can get some idea of this by looking at the different limits. So you see, if pi lambda is small, it looks like the numerator becomes small, but you see the denominator will also tend to 0, right? Because you see tan h and pi h approach each other as it goes to 0. And if you take the limits, you will see that this term actually becomes, it reaches a finite limit, but one that is larger than 1 by 16. Another thing you could do is just plot this function using any standard software, either Mathematica or you go to MATLAB, take different values for lambda and just plot this. And you should be able to show that it does the dependence of E versus, so this is 0 and then I have minus 1, minus 2 and so on. So this is the negative axis. It starts out somewhere negative and just becomes increasingly negative with pi lambda. Right, at large pi lambda, of course you will see that this pi lambda will dominate over time the tan h term. That would cancel, so you have minus pi lambda, which will be much larger than 1 by 16. So certainly at large aspect ratios, we should expect, at large aspect ratios, you expect E to go as minus pi lambda. So that's why you can see that I've drawn it as a straight line, because it indeed does. The asymptotic behavior is to decrease negatively and become increasingly negative linearly with pi lambda. But even in the limit of pi lambda going very small, which means you have very small surface roughness, because remember lambda is the aspect ratio. So let's just remind ourselves. So lambda is d by L. So if lambda is very small, it means that if I'm controlling only the waviness of the channel and keeping a constant gap, that it's the opposite of what I just said. If lambda is very small, it means that the wavelength is very, very, very large. So I have a gently wavy channel. So somewhere near here is where I have a gently wavy channel. I'm somewhere near here. So I have a modest correction to the flow rate, but one that is negative. Whereas now if lambda becomes very, very large, it must mean that L becomes smaller than D. So I actually have a sharp surface roughness. And you'll actually have a greater influence of the flow rate, a greater decrease of the flow rate in that case, provided of course you maintain the same value of epsilon. Okay, so can we understand these results? Well, one way to think about this, now that we have seen the result from our calculation, we can think back and convince ourselves that it makes physical sense from the following perspective. So I've kept the pressure drop on across the channel the same, right? That is value of constant G. The perturb pressure simply adjusts to the waviness of the wall to drive the circulations. So in a sense, if I do an overall momentum or overall energy balance on the problem, the input force I'm giving the problem, or consequently the input energy I give the problem, is the same, right? It's governed by the applied pressure gradient. So for the same applied pressure gradient, if epsilon is 0, I have only unidirectional flow. On the other hand, if epsilon is finite, the same applied pressure gradient has to drive not only the flow in the x direction, but also the flow in the y direction. So the added component of velocity in the y direction basically is coming at the cost of the x directional flow. From an energy perspective, the fact that you now have gradients in the flow in the x direction as well in the y means my viscous dissipation is going to increase. And so from an energetic perspective, I'm losing more energy to viscous dissipation, and consequently the total flow rate I get of the problem is reduced. Of course, these are kind of heuristic calculations, not very rigorous, but it makes sense to kind of come back and understand the problem in this qualitative fashion after, of course, we have got a rigorous result on which to stand and make such physical arguments. Okay, so that brings us to the end of this nice problem. We have not fully solved for the fields, but that is part of the elegance of the method, that in this problem it allows us to get to the result we are interested in, that is the flow rate, without having to determine all the fields. Even though the flow rate came at second order, we didn't have to complete a full second order perturbation calculation, because we could take advantage of the structure of the problem to obtain that calculation. But besides that, which is a peculiarity of this problem, the overall perspective of the problem has been to demonstrate the usefulness and the method of domain perturbation. The basic idea being that if you see a problem that looks complicated in the sense that the boundaries are complicated, the question you should ask yourself is, can you solve this problem approximately by writing it as a perturbation about a simpler problem on a simpler domain? So the same question is what you ask yourself in other perturbation problems as well, except there that the simplicity comes from a change in the domain equations. Here we are looking to solve this as a perturbation about a simpler problem where the domain is what becomes simple. So in this case, we recognize that we could get an approximate solution and understand at least the behavior, for example, how the flow rate varies for flow in a wavy channel by solving it as an approximation about flow in a flat channel, provided of course the amplitude of waviness is small. So with this in mind, you can also approach problems involving surface roughness, which could be this problem as well. I would just have to write an arbitrary surface roughness as a sum of various sinusoidal components, which I can do in general using a Fourier series or a Fourier transform. And then because the entire perturbation calculation is linear, I can add up the solutions to the different sinusoidal wavelengths of the wall to get a composite solution for to get the total solution for arbitrary surface roughness, which is why it's also useful to consider the sinusoidal form of the waviness of the wall. So what we've done is not specific only to a sinusoidal form. You can represent any solution to any form of roughness within the domain perturbation method. And of course for creeping flow where the equations are linear. So with this in mind, now when you see other problems or you encounter other problems where it seems like the domains are complex and that you know that you could solve the problem if only the domain had a simpler form, well then simply represent the complex domain as a perturbation about the simpler domain and then carry out a domain perturbation. Now in this course, we won't spend more time on such problems, but we will encounter the idea of domain perturbation, or rather one would also encounter this idea when dealing with deforming interfaces, provided the deformation is small. Again, we won't do that in this course because we're focusing on single phase flows, but it is a powerful idea that you will encounter again and again, which is why I thought it would be nice to introduce it at this point. Okay, so with that, let us conclude this lecture on domain perturbation, which is a nice way to round off the sequence of examples we've looked at in fluid mechanics where we can get approximate solutions using perturbation series. So with that, I thank you, and we'll now look forward to applying this as well as scaling methods to a range of different problems, and along the way maybe picking up some more interesting techniques. Thank you.